All right, my physicists, this is a recap of our simple harmonic notes that we took in class, or maybe that you missed when we took in class. And you do have a notes sheet for this that you want to take a little bit of time to use. So we learned about how the period of a simple harmonic oscillator is related to amplitude. We learned that it's not. It doesn't really matter how much you displace the oscillation. You still have the same period of the oscillator. We looked at mass and noticed that there was a relationship between the period and the mass of the thing that was oscillating. We also noticed that there was a pretty complicated relationship with the spring constant that we noticed was a inverse square root. And so what this looks like mathematically is that our period of a simple harmonic oscillator that is a spring with a mass is equal to 2 pi times the square root of the mass over the spring constant. And so this dependence is pretty useful. It helps us understand, like, yes, we did see this relationship with mass. We did see this relationship with spring constant. We didn't actually see the square root dependence with mass, but that's okay. We noticed that there was a proportional dependence on the mass of the object. And so we also started looking at graphs. If we look at the position time graph of a simple harmonic oscillator, we notice that the object displaces at a maximum, goes back through the equilibrium point, then goes to a minimum displacement, and notice that these two displacements are in fact the same value, just in opposite directions. So then we can actually look at the velocity time graph from this by looking at the slope of the line. And similarly, so we see this is a positive slope, so that means it's a positive velocity. Here we'd have zero slopes, that'd be a zero velocity, and so on. We can do the same thing to look at our acceleration time relationship by looking at the slope of the velocity time graph. And we get this interesting graph that is in fact a reflection over the x-axis of the position time graph we had. Again, when you're trying to address this yourself, it's really helpful to do those easy points first. So be able to say, the slope is 0 right there. That means that the velocity is 0. We can say that the slope is 0 here. That means the acceleration is 0. So those easier points, I think, are nice to do when you're trying to translate this type of graph. And we'll continue working on that as we go. But we also saw this other weird graph from our lab. And it was kind of funky looking, kind of messy, when we graphed the acceleration versus the displacement. And this actually relates to this inverse pattern that we're noticing here between them, or reflected pattern. And so what we're noticing here is that when our displacement is positive, our acceleration is negative. When our displacement is negative, our acceleration is positive. And this relates directly back to that really fundamental one we definitely want about what to force. So you know F equals ma. So that means that if I'm looking at acceleration, that relates directly to that net force. So a restoring force on any simple harmonic oscillator is opposite to the position, or to the displacement. And so that means it has a negative slope. So when x is positive, a is negative. And we can go with the opposite is true as well. And the other key thing is that the restoring force is proportional to the position. And it's a linear fit, so that means if there's 0 displacement, there's 0 force. So if we're at 0 displacement here, we have 0 acceleration, which means we have 0 force. And so you're definitely going to want to write down these details about the restoring force. And again, this is what defines simple harmonic motion as simple harmonic motion. So from this graph, we can actually find some pretty useful information. We can find the maximum acceleration, and that means also the force, because you just need the mass then. We can find the maximum displacement, or the maximum amplitude, and so that's this furthest point out. And again, notice that this graph does not continue on. It really is a bounded graph. So that means we have our maximum displacement. We can also look at the slope. So if we look at the slope on this graph, we're going to have acceleration is meters per second squared. Then we're going to divide that by meters. The meters will cancel out, so we get some units on our graph, on our slope, that are seconds to the -2, or 1 over second squared. So what does that mean? If we go back to this relationship between period and frequency, we notice frequency is inverse seconds. And so maybe that is what's relating to the slope, and it is in fact. So the slope here of this graph is actually 2 pi times the frequency squared. And this is called the angular frequency, omega. And our angular frequency means that it is the angle in radians a thing goes over time. So 1 full cycle, that's 2 pi r. 2 pi radians. And so 2 pi radians is 1 full cycle, and that is what we have here. And then times by the frequency means it's dividing by how many seconds it takes to do that. And so our slope is equal to 2 pi times the frequency squared, and that's the same thing as omega, 2 pi as omega squared, so 2 pi times the frequency. And so we can even connect to circular motion and say that, well, if we're going to think about this simple harmonic motion as a cycle, as the object bobbing up and down and up and down and up and down, we can relate that as the acceleration is equal to negative omega, this angular frequency squared. I'm going to grab this simulation because I think it's going to help clarify a little bit for you. So this website has some nice GIF simulations, or GIF-like simulations of simple harmonic motion. So lots of things are simple harmonic motion. But this is the one that I think will hopefully be the most illustrative of how simple harmonic motion actually can connect directly to circular motion. So notice that we have a mass on a spring, just like we looked at in class. And that as we are following the height of our mass, that's actually following the path of our object as it goes around in a circle, in circular motion. And so this is then tracing out our position time graph, which is sinusoidal, which makes sense. And it also makes sense from our breakdown of vectors into x and y components. Because if you look at just the y component, that's looking at the sine of theta. And so sine of theta, this is a sine curve. Hey, that's pretty cool. And so again, we can look at simple harmonic motion using our position, velocity, and acceleration graphs. This is really nice because it's giving you that clear look at the slope of the line. It's the slope of the line that is changing. So these are pretty groovy. So your task now, that you have this relationship. We know that our acceleration displacement graph is equal to, acceleration is negative angular frequency squared times the displacement. So the acceleration is proportional to the displacement and negative to the displacement, opposite of the displacement. So again, our restoring force, if that's true of the acceleration, then that's true of the restoring force as well. It's opposite to position and it is proportional to the position. So what I would like you to do is actually really check out simple harmonic motion in terms of energy. And this is something that I thought we'd already done in class and we haven't gotten a chance to do yet. So you're going to take a little bit of time to think about a first energy qualitatively. And so you're going to make qualitative energy flow graphs for a system that looks just like this. And so notice that the system actually displaces all the way to A, and then it goes back and forth. You can imagine it oscillating back and forth. And so you don't need to calculate at this point. And then you're going to practice some calculations with this system on the very back of this stapled packet, because it's going to really help you connect our knowledge of simple harmonic motion with this idea of energy, which then will connect to our continued learning around waves. So folks, take a little bit of time to give it a shot, and then you are going to take a picture of your simple harmonic motion worksheet and turn that in here on Schoology. Thanks very much, physicists. You got this.